Log on, tune in, find out. Another good idea from Cambridge.
Good afternoon. Professor Ragoucy will speak on nested Bethe ansatz for spin chains. Thank you.
Thank you for the invitation. So I will speak about nested Bethe ansatz, as you can see, and I must say I'm a physicist more than a mathematician, so maybe it will be a bit different from the talks you heard up to now. So the presentation is based on two papers done with my PhD students, Samuel Belliard, who is here also, and you have the reference there and there. Yes. So the goal of the calculation is to build eigenvectors for a transfer matrix, which I will define later. This transfer matrix being associated to integrable spin chain models. The most general one you can work with, at least the most general we can work with. The framework is Bethe ansatz, as it has been defined by the Leningrad School. And the spin chain we will consider will be closed spin chain based on these algebras. So GLN or GLMN, fine, Youngian, more, and deformation of these algebras. And also open spin chains based on the same algebras with diagonal boundary matrices. So I will present the calculation for the eigenvectors, but we will also obtain the eigenvalues, the Bethe equations, of course, and I will end with a trace formula for these Bethe vectors. So the plan of the talk, as I said, there is two big class of spin chain I will work with, the closed one and the open ones. So I will first speak with about closed one. I will present the spin chain in an algebraic framework. Then the algebraic Bethe ansatz, which work for spin chain based on SU2. And then the nested Bethe ansatz, which is a nesting of algebraic Bethe ansatz, which works for bigger algebras. And end with the trace formula for the Bethe vectors. And then I will redo it for open spin chain in a faster way, and then conclude. So, yeah. So first, the spin chain. So I start with the simplest ones, the XXX and XXZ models, so which describes in physics interaction of spin 1/2 on a periodic lattice, one-dimensional lattice. So it's a closed spin chain because the lattice is periodic. And so the chain itself is represented by these tensor product of C2 spaces, L C2 spaces if you want to deal with a spin chain with L sides or quantum spaces. And the Hamiltonian acts on two neighboring sides, so two C2 copies, so J and J plus 1. And you have the periodic condition. We identify the site L plus 1 with the site 1. The form of the Hamiltonian is written here. So for the XXX model, it's just the scalar product of polymatrices at site J and site J plus 1. So it's a spin interaction. And for XXZ model, you have an anisotropy parameter which show up, which is written there as a function of Q, the deformation parameter of the algebra, which will show up. And so what we want to do is to compute the spectrum of this Hamiltonian, H, acting on this spin chain, and find its eigenvectors. So to do
sorry, what was delta?
Delta is just a number related to Q, which will show up as a deformation parameter in a UQ SL2. So it's just a number which measure here the anisotropy when you make the scalar product if you want. you have a preferred direction in the Z, the Z direction, yeah. Okay, so to compute these eigenvector and eigenvalues, you introduce the monodromy matrix, which is a product of so-called R matrices that you have heard of, I guess. So it acts on the quantum spaces, the sites 1 to L I was speaking about before, and plus another auxiliary space, which is also C2, but which is not related directly to the chain. So this monodromy matrix, so it's a tensor product on the space, the blue space if you want, and it's a matrix product in the zero space, the red one. So this monodromy matrix obeys RTT relation, so-called RTT relation, with the same R matrix as the one there. And here you have the R matrices related to the XXX model or the XXZ model. And U is just a spectral parameter, a complex number. So that's for the monodromy matrix. Then you can introduce the transfer matrix, which is just the trace in this auxiliary space of the monodromy matrix. So it acts only now in the quantum spaces on the site. And all this leads again to the Hamiltonian using the logarithm derivative of this transfer matrix. So that's the reason why we introduce all these things. This transfer matrix contains the Hamiltonians in when you develop this transfer matrix as a series in U. And from this relation, you can compute that the transfer matrix with different values of the spectral parameters just commutes. So in this way, you have a series of Hamiltonian, if you want, commuting Hamiltonian, or of conserved quantities for this Hamiltonian, which are hidden in this transfer matrix. So again, from the spin chain, we had this RTT relation, and in fact, everything comes from this relation. We have integrability, which means that you have commuting transfer matrices. I will show you that it leads to the calculation of the eigenvector of in fact, the transfer matrix, more than the Hamiltonian, and the Bethe ansatz equations. And from the algebraic point of view, here you know that this is just an FRT presentation of the Youngian for the XXX model, because the R matrix was associated to the Youngian of GL2, or for the quantum group UQ, affine UQ GL2, because for the XXX model, because R matrix was related to this algebra. So, of course, here you know that this presentation, these RTT relations codes the the commutation relations for these algebras. And in fact, here the spin chain, the monodromy matrix associated to the spin chain, is just a representation of this algebra constructed from the tensor product of L spin 1/2 representation of SU2 or UQ GL2 when you deal with XXX.
Is there a reason you're using GL2 rather than SL2?
No, it's just I'm lazy. No, it's here I'm at the level of the algebra, so I don't look really at all these things. I mean, I'm just in general I use in fact GL2, but for spins physicists use SU2, so sometimes I write SU2, but it's SL2 or GL2. So generalization from this, since you have just RTT relations with monodromy matrix represented in some representation of GL2, the generalizations are quite obvious. either you change the representation, so instead of taking L spin 1/2 representation, you just take different representation of the same algebra, or and then it will change the dimension of this quantum space, of the space on the chain, or you change the algebra itself, and you consider R matrices, for instance, coming from different algebra that I will just call A, M, N.
What do you choose for the Hamiltonian?
The Hamiltonian is here, it's always the same.
Oh.
Because since you have always this relation, you will have always commuting transfer matrices. So you have a set of Hamiltonians inside this transfer matrix, and you can take this one as a Hamiltonian. It will not be local anymore. I mean, there will be interaction with more sites within, but it's an Hamiltonian. So yeah, exactly. So you have an Hamiltonian describing spins, which now are just representation of a given algebra on a periodic chain, so on a one-dimensional periodic lattice. So that's for the framework for the spin chain. Now, how to construct again the eigenvector of this Hamiltonian and more generally of this transfer matrix. So you use the algebraic Bethe ansatz. So I come back to the XXX to be more simple, but you start again with the monodromy matrix. And for the moment, I just expand the RTT relations, expanding the monodromy matrix into its components. So it has 4 components. And the transfer matrix is just the trace, so A plus D. And you can compute, using the RTT relation, the relations between ABCD, among ABCD. In particular, you can see that you get this kind of relation where F, G depends on the R matrix you started with. So they are just functions, but you can compute them. And you can see that A and D are like Cartan operator, and B and C are like ladder operators. So the construction of the eigenvector starts with a reference state, which is just the highest weight, in fact. So it's a state which is annihilated by C. So it makes the monodromy matrix triangular, and it's an eigenvector of A and D. So it's an eigenvector of the transfer matrix. And then we just act with the B operators on these reference states to build eigenvector of the transfer matrix. So we start with what is called a Bethe vector. So a series of B's acting on this reference state. And then we compute the action of the A and D operator on this state. So there is, from the commutation relation which were there is one part there which just gives you an eigenvector, say, plus terms, which tells you that in general it's not an eigenvector. So I don't want to give you the exact expression, but just for the idea. So you have these two parts, and you ask phi to be an eigenvector. So one way is to cancel these two terms, since the transfer matrix is the sum of these two, A and D. And if this sum is 0, so if in fact this is 0, then you have an eigenvector. And in fact, these are just the Bethe equations. You can, using the exact expression of P and Q, you can compute that it takes this form. And where W now, which was coming from this W in A and D, as disappears. which show you that in fact you have an eigenvector which is common to all the transfer matrices, whatever W is, and then you have this part which is just the ratio of entries of the R matrix, so it comes only from the algebraic part, and this part comes from the action of A and B on the reference state. So it's linked to the representation you started with. So just to sum up, the Bethe vector, you started with this expression. You got, and you construct them as eigenvector of the transfer matrix using only commutation relation of A, B, C, D. So of course it's valid for any representation. And you need a reference state, a highest weight representation. And you get the Bethe equations and the eigenvalues of this vector with respect to the action of T. And the form of this vector does not depend on the representation, since you were just using commutation relation. Now we want to extend this to the case of larger algebras. So you start again with this RTT relation, but now the R matrices which are there are just the R matrices defining an algebra, the Youngian of G element or UQ G element. And you start as for the SU2 case, so you divide the monodromy matrix in two, but now you keep A as a scalar for the auxiliary space 0, but now of course you have here vectors, one line, and a big matrix here of size m plus n minus 1 square. The transfer matrix is is A plus the trace of D. And then you can compute again the commutation relations coming from this for A, B, C, D. And in particular, you can see that for the action of A on B, it's exactly similar to the SU2, to the 2x2 case. Here you have R matrices appearing when you want to commute B with D, because you deal with matrices and vectors.
Sorry, what's FRT again?
It's RTT, it's Frenkel-Reshetekin-Taktayan presentation. Frenkel-Reshetekin-Taktayan presentation.
Bethe, yes.
Feigen. What? Feigen. What did I say?
Bethe,
Faddeev, yeah, sorry. This is what I call also RTT. Sorry. Yeah. So this developed on using this decomposition of the monodromy matrix gives you some relation. These are part of the relations. You have a part which just tells you that A and B commutes as usual as for the 2x2 case. Here you have how to exchange B with D, which is becoming more complicated because the R matrix of a smaller algebra is appearing. It's the same type of algebra as the one we started with, but with a rank less by 1. And this algebra is just here, and it's just the D operators which obey this relation. So we can try to mimic the case, the 2x2 case. So we start with some state, I will speak about later, and we act with the B operators. But of course, the B operators, now you have several types of B operators, since you had a line vector. So omega there will have an index, and you sum over all the indices to take care of all the b's. And also here, since D now is a matrix, you have also creation operator hidden inside D. So if you write something like that, you're losing a lot of creation operators. So you just assume that they are hidden in this omega vector that you don't know, except that it is built from a highest weight state of the algebra, AMN you started with, and the creation operators hidden in D, in the matrix D. So just assuming these two things, you can compute the action of the A operator, and you can just show that A is in fact, omega is in fact an eigenvector of A, whose eigenvalue depends on the highest weight and also the commutation relation of A with D. So with this, you can compute the action of A on the full state here, and you get exactly the same kind of expression as you had in the 2x2 case. So you have the part which looks like an eigenvector, and the unwanted term, which are exactly the same, the same form as in the 2x2 case. However, if you look at the action of the trace of D term, then you have a term which is like the eigenvector, but here you have something which looks like unwanted term, except that now you have this part, and in this part you can recognize the transfer matrix of a new chain which is built from D and from R matrices of the algebra of rank m plus n minus 1. And omega tilde is just constructed from omega with some vector there. So you see from the difference with the 2x2 case, where the unwanted term took this form, is just this part. And this is just where the nesting appears. You end up with a new problem, which is to compute an eigenvector omega tilde from this new transfer matrix, which was built from the D terms and R matrices for the AM and A-1n algebra. So it is still the same problem, except that you lower the dimension of the algebra. But here you can see that since D is acting on the site 1 to L, and you have more matrices, you have a chain which is of length L plus M1. M1 was just the number of B operators there. You can show that this new monodromy matrix there obeys the FRT relation for the algebra, this smaller algebra. And of course, you interpret these R matrices as new site on this for this chain, new chain, and you are allowed to do that because, in fact, this R matrix is just as a monodromy matrix with one side for the algebra. So you can iterate. Once you have since you have the same problem, you can divide again the transfer matrix. Then you will have a term A, a new term A, a new term D. The term A, you can compute it. Omega tilde, you will build up as the B operators acting on some new omega term, which will be constructed only on the creation operator in D2 and on a reference state. But now the reference state will not be only 0, but 0 tensor all the highest weight coming from the fundamental representation you had in this new chain, the new sites you add. And then you can iterate. So it's a bit calculation, but okay, just to summarize. You started with a chain of length m. You had an algebra, AMN, a reference state. Then you divide in this way the monodromy matrix, and you, at the first step, you end up with a chain, a new problem based on a chain of length L plus M1, but for an algebra which is smaller, and the reference state now is becoming of this form, where here you recognize the highest weight of fundamental representation for this algebra. And you go on. At step K, you will have an algebra of this form, a chain which is longer, and a reference state which has more sides. And the Bethe vector will just be the product of these B operators coming here from the A algebra, then here from this algebra, and so on, up to the n, where the last ones are just in the lower corner of the starting matrix, and they act on this reference state 0, m plus n plus 1, n plus n minus 1. So that's the reference state. And again, the B operators, you have less and less B operators because the algebra is smaller and smaller. So with this expression, you can see that you have a recursion relation, which is quite obvious here, which allows you to construct the Bethe vectors of the chain on the AM chain from the Bethe vector from the AMN-1 chain, and using this recursion relation between Bethe vectors, can show that in fact they can be re-expressed in this way, where now here you have the monodromy matrix acting on the chain, the initial chain of length L. You have m copies of this monodromy matrix, where m is the sum of all the mi's, so all the number of B operators you were using to construct the Bethe vectors. And so here you just have, instead of the B vectors, B operators, you have the full monodromy matrix. Then you have a bunch of R matrices, which were the R matrices which were appearing. Yeah.
Quick question. So,
Yeah.
so your procedure involves passing through a logic chain.
Yeah.
Does it involve solving different Bethe equations, or the equations remain the same? You
No,
need to solve the
yeah,
equations
yeah.
to get the eigenvectors, right?
You have some auxiliary form of for the Bethe equations. Each time you have a Bethe equations, and
so
then
do you get more Bethe equations, or they're just basically the same?
no, they are basically at the
Basically
end
the same.
they are the same. Yeah, yeah.
So you don't need to make this chain of equations to make it.
No, I mean, you are, with respect to the 2x2 case, you have only one type of Bethe equations. If you take SU3, for instance, you will have two types of Bethe equations, but that's the usual thing.
Mm-hmm.
It's just you get at each step, you get a new form, new equations, and then when you collect everything, you just get the usual Bethe equations in this way. Okay, so yeah, the form of the vector, the Bethe vector. So here you have the monodromy matrix, and it's as the B's acting there. Here you have the bunch of R matrices which were coming from this new auxiliary fundamental representation we were using in the recursion. And here you have these elementary matrices, so it's just elementary matrices of size m plus n with 1 at position here to 1, let's say. And they just, in fact, they play the role of the fundamental, the highest weight for the fundamental representation, and also they will pick up in the trace. They will pick up just the B terms, in fact. So it's just a re-expression of the previous form there, but as a trace formula. So you have a bunch of B's, and here you have a bunch of T's, but the t's are just in the algebra. So here you have all the R matrices which were appearing in the calculation, and here you have these elementary matrices just to pick up the right term in this product, and then you act on the reference states. Using this expression, then Tarasov and Varchenko were able to show that there is a coproduct property for the Bethe vectors of this form. So if you take a representation which is a tensor product of two representations, then the action, the Bethe vectors built for this state is just the tensor product of Bethe vectors built for these two states up to a summation on n and m. So these are just the indices here which were appearing, which were just labeling all the b's you were using to create the vector. So you sum here for n lower than m, so it means just that the vector n minus m must have only positive entries. And you have also a Q symmetrization in the variables u, the variables which were used there. Okay, so that was for the closed case. Now the open case, just so the Hamiltonian here it's almost the same, except that you don't have a periodic lattice, but a one-dimensional lattice with boundaries. The Hamiltonian, it changes this way, so you don't have the last term because it's not periodic, but you have interaction of the first and the last sides with some external fields, boundary fields. But for the bulk term, the Hamiltonians are the same. And in fact, you can describe this again using monodromy matrices. But now you sorry, you need two boundary matrices which will reflect this boundary field, which interact with the spins. And these boundary matrices will obey the reflection equations of this form. So R is again the R matrix I was using before. R bar is just the same R matrix, but with the second spectral parameters inversed in the sense of minus u for Youngians and 1 over u for quantum groups. And this is for the first boundary matrix, and the second boundary matrix obeys the same kind of relation, except that you can deduce using this relation. In fact, K plus is not forced to be equal to that, but it must obey the same relation as you deduce from this relation and this reflection equation. So it's a dual reflection equation. So from these two boundary matrices, you construct a new open chain monodromy matrix, which is built from the monodromy matrix we were using in the closed case, the K matrix, and then again the same monodromy matrix, but inverted and with the spectral parameters inverted also. So it's based on this, and you can show that it obeys the same reflection equation as the K matrix, so this one. And now the transfer matrix, which will be just a trace of the K plus matrix by this monodromy matrix. And the Hamiltonian, again, will be the derivative at u equals 0 of this transfer matrix. Using the reflection equation and its dual form for K plus, you can show that this transfer matrix, transfer matrices commutes for different values of the spectral parameters. So again, you can look for common eigenvectors for all these transfer matrices. And you will get also, of course, transfer eigenvector for the Hamiltonian. So algebraic interpretation, again, so you can forget about the representation and use just as a definition this reflection equation for a S matrix, a monodromy matrix built on the just the monodromy matrix for the AMN algebra with inversion with the K matrix, and you construct in this way a reflection algebra, which is in fact a co-ideal of the AMN algebra, the one which was used in the closed case, and the physical interpretation is the same. So you construct this monodromy matrix from the closed case monodromy matrix plus a boundary, and the transfer matrix will use the K plus matrix. So you need the two boundaries plus the bulk just to define the open chain. So you have commutation of the transfer matrix, and this construction is valid for any K plus or minus matrices, provided they obey the reflection equations or its dual form for K plus. For the algebraic or the nested Bethe ansatz, you need to take diagonal boundary matrices. It's not within the construction, but within the construction of the monodromy matrix, but it's forced. You are forced to do this to do the algebraic Bethe ansatz. So I will restrict to this case.
Excuse me, K plus more is the same
No. I did not write the K plus. If you use this formula, so K plus behaves as K minus transpose, in fact, with a shift and so on. So you can deduce the reflection equation for K plus. And so that's what I call the dual form of the reflection equation. Okay. And you need these two relations to prove that the transfer matrix commutes. So again, you start with, for the algebraic Bethe ansatz, so the 2x2 case, you start with the monodromy matrix that you decompose in this way. The transfer matrix takes this form, so now you have the K plus and the two entries of the K plus matrix. You can compute the commutation relation using the reflection equation. They take this form. So with respect to the previous case, you have these two terms which were not there, plus this one, and this one is particular because it breaks the symmetry between A and D. You see, there is this additional term. But again, you can see that A and D act as Cartan operators, and B and C will be the ladder operator. To suppress this term, you need to make a change of basis of this form, and then you get this. So again, it's not the same relation as in the closed case, of course. It's not the same algebra, but it's symmetric between A and B hat. And now you can do the same thing as before. So you just act with the B's on the reference states, which will be an eigenvector of this A and this D hat. And this beta vectors, when you compute the action of A and D hat on this, have two terms, the unwanted terms, and if you add these two, when you make the sum, if you require that this sum is 0, then phi becomes an eigenvector of this transfer matrix.
Does this process give all eigenvectors?
Sorry?
Does this process give all the eigenvectors? I mean, you would make this extra assumption of the individual terms. 0. Can there be other ones where that doesn't happen?
It's believed that it gives all the eigenvectors. It's not proven except in some cases, but in general, when people do numerical calculation, for instance, it gives all the eigenvectors in this way, and there are proof for special cases, but in general, no, it's not proven that it gives you.
Well, this is 2x2 case, you can see.
Yeah, for two. Yeah, I was speaking in general, but for 2x2, yeah, you can see.
So which boundary matrices K you use? Maybe I missed.
Sorry?
Which boundary matrices do you use?
Diagonal ones, but I didn't write them. But it's diagonal, so it's a yeah. For the moment, I just assume that they are diagonal. So I mean, it's the diagonal K matrices which solve the reflection equations. So it depends on the algebra you use, but they are of the form u minus some free parameters over u plus some free parameters, something like that. And then diagonal, and you change.
You can classify all of them? Or
Yeah, they have been classified, yeah. Not by me, but they have been classified. They are for diagonal ones, they are classified for long ago. For non-diagonal ones, for the Youngians, they are classified. For the Youngian based on GLN, for UQ, there are results. I don't know if there is an exhaustive classification.
No, they classify some of them.
Some of them, yeah. It's
but
not
but
exhaustive,
these
I
are
think.
affine. These are with spectral parameters.
No, Naomi was a finite case. It
This
was
is
Letzer
affine.
then who was considering, Gail Letzer.
I know, yeah, but this is affine. So they depend
But-
on you, yeah?
Yeah, they depend on you, yeah. No, but there are, I think that for the Youngian, I'm sure that there is a complete classification because in fact, you can show that the solution, the K matrices commutes. So you can diagonalize them, commutes for different values of spectral parameter, for the Youngian, of the spectral parameter. So in fact, you can diagonalize them in the same basis. So if you know the diagonal solution, you know everything.
And where is this written? Is there a paper?
It's in one of our paper, but I can give you the reference. The point is that the K matrices are diagonalizable in the same basis. The K minus, for instance, the K plus, but then you don't know if the K plus and the K minus are simultaneously diagonalizable. If you assume a new reflection equations which connect the two K plus and K minus matrices, but I mean, you just have to assume that these relations hold, then you can prove that it works. But okay, so that's what. So diagonal matrices. So yeah, you can compute the action again same way, and you get the Bethe equations. And again, if you just simplify the polynomials, you can compute. You see that in fact the relation does not depend on W, so it's a good thing. And you can divide in three parts the Bethe equations: the part which is algebraic, which comes from the reflection algebra, the part which comes from the K plus and K minus matrices, and the part which is linked to the representation, the highest weight 0. There we started with. For the nested Bethe ansatz, again, I don't want to enter into the details again, but you start with the reflection equations. You divide the monodromy matrix, then you have a scalar part and a matrix part, and you do the nesting. Again, you have to be careful to change basis, and the change of basis is almost the same as in the 2x2 case, except that you have to make a shift on the spectral parameters. And this change of basis is essential if you want to recover the algebra at the lower rank, at the dm-1n algebra. So again, you construct the Bethe vector in this way with some omega terms, and what you can show, that's the difference with the closed case, is that the d hat operators obey also the reflection equation for a smaller algebra, but not in general, but you need to apply the operators on these omega terms. So it means that just the reflection algebra d m-1n is not embedded in the dmn reflection algebra, but you can obtain it just from using a coset construction. And in doing so, you need to further restrict the K plus matrix and to take this part, to take it of this form, where K of u is just a function or 1, it can be 1 also. So, in fact, so up to now we were supposing that the K matrices were diagonal. For K minus, we keep it just diagonal as usual, but here you need to take this form. Although that in the other way to compute the eigenvalues of the transfer matrix, when you use the analytical Bethe ansatz, you just need to say that K plus is diagonal. Here you need this to perform the calculation, and it leads you to the trace formula, which now takes this form. So you have, again, this bunch of S, which will be all the B's acting on the reference state. Then you have R matrices, but now since the S matrix is of the form T and T inverse, you have the R bar and R matrices appearing here and here, so a bunch of R and R bar. And again, you have these elementary matrices. We just select pick the right term to construct the eigenvector. So we are at this point for the moment. Just to stress that here the K plus matrix does not appear. So even if during the calculation we need to take the special form for the K plus matrix, it may be that this form is valid whatever the K plus matrix is, diagonal of course. And then we need to do the coproduct property, but for the moment it's not done. So just to summarize, so I've presented you a construction of the transfer matrix eigenvectors. So for these, it's a mistake, it's Youngian here. For closed spin chain based on, so the Youngian based on GLM or GLMN, for UQ or on GLM or UQ on GLNM, and for the closed case, and for open spin chain for the same algebras but and boundary diagonal matrices, and use analytical Bethe ansatz. So we computed the transfer matrix eigenvalues, the Bethe ansatz equations, and also the Bethe vectors, and we have a trace formula for that, for these. So what remains to be done? So we need to compute this coproduct property for the open case. So we are computing this. What we want to do is to compute the scalar product of these Bethe vectors, because what we aim to do is to compute correlation function, and we need first the scalar product, and this maybe will be easier to do, or surely will be easier to do using current realization, as it has been done by Koroshkin and Pakuliak, at least for the closed case. Now we need to, for the open case, nothing is known. And then, so we aim at computing correlation function, as most of these people have done. The QKZ equations that appears when you want to compute the correlation function. And also there are problems which were not touched by this construction, the case of non-diagonal boundaries. So there are some ways developed by Bazeyak and Koizumi using Q and Sager algebras. There are also these Chinese people who developed gauge transformation to get rid of the diagonal, non-diagonal case. And also there are also all these non-highest weight representation which we cannot deal with, and so maybe separation of variables a la Sklianin or TQ relation may solve this. That's it. Thank you.
Any questions?
Seems to me the most basic open question is why this ansatz works at all.
Why it works?
Yes. I mean, why should it produce all the eigenvectors?
Because it's like it's really like you start with the highest weight representation and you act with ladder operator, so you generate almost all the vector of the representation. So maybe you need to be in an irreducible representation, and there are cases where you need a second reference state because the representation is not irreducible. But how
Does this lead to a proof that you have all?
No. I said it's conjecture, but
that
it's
seems to be the
natural.
most important problem. Show that I'm not absolutely sure the problem is well defined. Is it you're working on an infinite dimensional vector space ultimately?
No, they are finite dimensional.
Oh.
I mean, okay, maybe you can do the same construction for infinite, but then, yeah, it may be more difficult, and completeness, I don't know at all. Yeah. But the point is to find to diagonalize the transfer matrix. So you find the beta vectors, it works, and
But why?
yeah, it's a good question, but in the spirit, it's because you just construct. It's a kind of Gelfand-Zettling basis, I think. Because you act with the bees which were up, and then the nesting is almost the same. But it's not a proof.
Any more questions? Yeah. Oh, yeah.
In what cases can you prove the existence of the Bethe ansatz equations? This is really related to the previous question.
Prove the existence, but once you have computed them, then.
Well, but you compute them on a computer, you say.
No. It was for completeness that some calculation were done. If you consider a spin chain with a small number of sites, you can just compute the using computer. You can compute the eigenvectors of this. It's a huge matrix, but if the number of sites is small, then you can do it. So you can compute all the eigenvectors. And then you can look at the Bethe equations you have, you solve them, and you compare, and it's okay.
Yeah, but you would like to have an analytical proof that there are as many solutions as the dimension of the
I agree. There is no proof for this, but you can always compute you have always the Bethe equations. So you're sure that you have eigenvectors. The point is completeness, not the existence of the Bethe equation.
Can you use degeneration to Gaden model to show that it generates all eigenvectors?
With what?
I mean, you could degenerate this to Gaden Hamiltonians. Yeah, is this correct?
Maybe this I'm not sure. Yeah.
And for them, there are some results about
It's
this.
true.
So maybe you can use these results and deformation arguments. I think.
Maybe.
It was possible they would do it from the beginning.
Yes.
Yes.
What is is there anything physical that the parameter Q corresponds to?
Yeah, that's the anisotropy. So it's really in the Hamiltonian. Here, at the beginning. Yeah. So you see, so delta here is really in the Hamiltonian. So it's you have the z direction which is different from the other ones, and here q is there. Delta is just q. So that's
So there's nothing like a magnetic field or anything that you...
Yeah, it's a uniform magnetic field.
Well, you could have delta surveys, huh?
Delta, there are models, X, Y, Z models where you, but then the algebra is becoming more and more complicated. But yeah, sure.
Did you study effects when Q is the root of unity? What happens?
No, I didn't. Yeah. In general, I think you can do the same thing for highest weight representation, but the cyclic ones, I don't know. They are not highest weight, so.
Any more questions?
Is there any relation between the boundary conditions that you have considered and the so-called twisted boundary conditions?
No, that's another approach, because what you get then is twisted Youngians, or the reflection equation is different. So you can do the same kind of calculation using twisted boundary condition. You mean open chain with twisted boundary condition? That's right.
I was thinking of the kind of thing that Algebraic et al.
I don't know this, but okay. Because there are constructions using something which is called. So let me see. Instead of the reflection equation. Oh yeah. Instead of this reflection, you change the R bar matrix, in fact, somehow. Instead of using, this is more or less, in spirit, this is the inverse of the R matrix, and instead of taking the inverse, you can take the transpose of the R matrix in one space, and then you have another model. But I don't think the algebraic Bethe ansatz have been done for this kind. Yeah, I'm quite sure, because in fact the solution for the chi-matrices, there are no diagonal solutions. So you cannot perform the algebraic Bethe ansatz.
Any more questions?